and welcome to this machine learning using Python course by Simplilearn. In this course, we will start with the basics of machine learning, how it fits under artificial intelligence and how it is different from deep learning. You'll understand how machines learn from data, find patterns, and make predictions. You'll then explore the major types of machine learning, including supervised and unsupervised learning. After that, we'll move into important concepts like regression and classifications, where models predict values such as sales or house prices, and categories such as spam or not spam, fraud or not fraud, and yes or no. You'll also learn key algorithms like linear regression, logistic regression, naive Bayes, k-nearest neighbor, decision trees, random forest support, vector machines, XGBoost, and also CatBoost. Along the way, you'll also cover data preprocessing, feature engineering, model evaluation, cross-validation, regularization, hyperparameter tuning, and ensemble learning. So you can understand how to build better and more reliable machine learning models. By the end of this course, you will know how machine learning models are built, trained, tested, improved, and applied using Python. So let's get started and learn how to turn raw data into smart predictions with machine learning using Python. If you're interested in mastering the future of technology, the professional certificate course in generative AI and machine learning is the perfect opportunity for you. This 11-month live and interactive program provides hands-on expertise in cutting-edge areas like generative AI, machine learning, and tools such as ChatGPT, DALL-E 2, and Hugging Face. You'll gain practical expertise through 15+ projects, integrated labs, and live masterclasses delivered by esteemed IIT Kanpur faculty. Integrated labs and live masterclasses. Alongside earning a prestigious certificate from IIT Kanpur, you'll receive an official Microsoft badge for Azure AI courses and career support to Simplilearn's Job Assistant program. Hurry up and enroll now. Find the course link in the description box below and in the pinned comments. Before we start it, here's a quick quiz for you to answer. Which type of machine learning is used when the model learns from labeled data? Is it unsupervised learning, supervised learning, reinforcement learning, deep learning? Comment your answers below. Let's get started.
What machine learning is, which is a subset of artificial intelligence, right? That's basically machines learning from data in order to make decisions, essentially. So this was a big departure from the rules-based system, right? We're explicitly programmed to make decisions. So just think of an example like a really big kind of if this, then that, then that, then that, and else if this, right? So a bunch of rules that had to be pre-programmed in order to come out with some final answer. With machine learning, it's the exact opposite of that. We're actually training something from examples from existing data in order to predict something or make some type of decision. And so we're going to learn about the various ways we can do machine learning. But if you guys remember, we talked about some of this, like the differences in the basically rules-based approaches to learning from data approach. And included in that is going to be complex unstructured data. So things like images, text, audio. What handles those really well is deep learning, which we will get to in the course after this. But those are certainly in there as learning from data, even complex data. So we had this picture, and I think this is kind of around where we left off last time, was just distinguishing between those three terms. We see artificial intelligence, deep learning, and machine learning kind of used interchangeably, but this is really how they fit in. Artificial intelligence is kind of a broad, anything mimicking human intelligence, which doesn't have to be learning from data, but machine learning is part of that. And then one way to accomplish machine learning is to use neural nets, which is the focus of deep learning. And so deep learning has found a lot of success, especially recently, with those complex data types like images, speech, text, right? So deep learning used all over the place, even in modern like generative AI, we see deep learning used quite a bit. It really anything that's using neural nets is going to be deep learning. And again, we'll focus on that later, but we're going to be mainly focused on machine learning for this course. Primarily machine learning that does not use neural networks, okay? So just models that are not necessarily neural networks. Be our focus. So in machine learning, we had an example of a game, essentially learning what decisions to make based on the kind of current state of the board. This could be a machine learning example that learns from many previous examples. So a lot of data around these games are used to train these kind of robots that can play these games and play them at a very high level. So there's been a lot of successes actually in machine learning and deep learning around uh, playing games like chess or Go using machine learning algorithms. So pretty cool. All right, so I think this is where we ended. Last time we said there's a bunch of different use cases for machine learning. So recommendation system is going to be a big one, and we will actually study that in one of our final lessons of this course. Chatbots, like generative AI doing sentiment analysis, chatbots we'll study later, but those are certainly an application of learning from data in order to generate responses to text prompts, right? Spam filtering, that's a good example, like classifying an email as spam or not spam. That gets trained from examples and learning from data, such as previous emails. Social media posts analysis is another kind of text data um, use case, but you can do a lot with that text. Like you can predict the sentiment, you can predict the category of what the post is talking about. Those kind of things all can be done with machine learning. And many other use cases not on this list that we will cover, as we go further. Okay, so this is where we kind of left off. So what's doing all the
Beginning
hard work
of
here
classes and all
is
that
the
important things to me.
machine learning algorithms. So these are things that will learn from the data. So they are basically um, algorithms or sets of rules that or mathematical rules, I should say, not formal rules like in the sense of a rule system, but mathematical formulas and mathematical rules essentially that help us learn from the data. So they correlate the data to some type of outcome. So some type of prediction, whether that's going to be, as we will see, whether that could be like a number, like we're predicting a price or demand or sales, or it could be a category, like is this transaction fraud or not fraud, or what's the probability that this is fraud? So we have different kinds of predictions we can make with machine learning. Um, but we will study the kind of the differences of those coming up. But machine learning algorithms are really what power, they're kind of the models, right? They're the models that help power machine learning to actually learn from data. So we're going to spend a lot of time in this course studying those algorithms, like the different models that we can build and what their differences are, what their strengths are, what their weaknesses are. We'll learn a lot about those. Okay, so as you can imagine, like everything is so data dependent, right? We're learning from data, so it makes sense that the quality of data really, really matters here in determining how strong the model can be. So you see this graph here charting kind of the high quality data versus just any old data, but a decent enough quantity of it. You can see that performance, and the performance is measured by some evaluation metric. So think of it as something like an accuracy. Like if we were predicting fraud or not fraud, how accurate can our model get at actually detecting fraud? Um, it gets better and better and better. And this graph shows that the higher quality of data that we have. So there's kind of that there's a saying in machine learning called garbage in, garbage out, What that means is if you have poor data, even the best model in the world, poor data is not going to result in having a good model that can be accurate and perform well. So it needs to be high quality, meaning there needs to be a decent amount of it, and it needs to be labeled appropriately, as we'll talk about. Um, and it needs to not have any, significant outliers. It needs to be clean, not have those missing values. All of those things, you have a good chance at deriving good predictions from higher quality data, as this kind of shows. Okay. So one thing we're going to learn as we go along is quantity matters as well. So not only quality, but a decent amount of it. And we're going to learn those kind of rules of thumb, like how much data do I need for certain algorithms. Um, One thing that we will see is that the basic machine learning models that we'll study don't need as much as a neural network would. Neural networks are going to require a lot more than a basic learning model. So that's something we will see as we go along. But this is something we'll talk about and discuss with each model that we study is kind of how much data do we actually need to produce a high quality model. Okay. Any questions so far? Okay. Let's talk about the different types of machine learning that we're going to discuss. There's going to be two primary ones that we will study in this course, and then a couple others that'll be a little bit more advanced that we won't get to, but worth knowing about. So there's going to be four total that we'll study or talk about, and they'll be on this list here, which is supervised learning and unsupervised learning. Now, I'd say the majority of our focus will probably be on supervised learning, and we'll talk about what that means. But we'll also cover unsupervised learning as well. And so we'll look at the most popular techniques in each of these types of machine learning. Um, and then we'll talk about these two, but not really study them because they're more advanced topics that will be beyond the scope of what we'll do. But these are going to be different styles of machine learning that are going to be characterized by um, what kinds of predictions they make, what kind of data they need and require, um, and what kind of outcomes they're actually producing. Um, so let's get into each of these. But the one that we'll probably spend the majority of our time on is going to be supervised learning, but we will study unsupervised learning as well. We'll study both, and we're going to define both of those coming up. And again, these will be a little bit more advanced topics that we won't spend too much time on, but we'll discuss their relevancy in machine learning and give a good definition to it. Okay. All right, let's start with supervised learning. Now, this is going to be a term that really refers to using examples. So using labeled examples. So here we say labeled data to help our model train. In other words, help our model be able to predict guided by specific input output pairs. So supervised really refers to the fact that we have answers, we have examples, we have answers with those, and we use that collection of data to build our model off of so that we can predict those kinds of things like a price, like a category, like a spam, not spam. In this slide, like we would be predicting if this shape is a square, a triangle, or a circle. Um, but but when we build a model for that, we have data that has an answer attached to it, right? We've talked about this before a little bit with labels. So there's a guide there that can guide us towards building our model. There's an actual every example has an answer, and that answer is really critical to help build our model off of. So that's it's almost like you have a bunch of exercises in, let's say, like a math textbook. You have a bunch of exercises and you have the answers, and that way you can kind of check your work. You think about model training, that is really a lot of that process of model training, as we are going to discover, is basically checking our work against these answers in our data, in our training data. Okay. So supervised learning is any type of machine learning that involves learning from labeled data in order to predict outcomes. Okay. Predict outcomes, like, now the outcomes can be numerical. They can be like a price, temperature, demand, sales, revenue. They can be numerical, but they can also be categorical. So they can be like spam, not spam, fraud, not fraud, cancer, not cancer. Um, Dog, cat, giraffe, those kind of categories. We could predict those. It's some type of outcome. Okay, some type of outcome. The key is we're using labeled examples to guide our model building. That's why it's called supervised learning. So we know in our data, we know what the inputs are, of course. Those are going to be, think of the inputs as like all of our columns. And then we have a special label column that represents the output we're trying to predict. So if you think about that housing price data, the label could be the price. And that's something we would build a model to predict. But we have answers for all of our examples in our rows. We have answers to help guide our model building. They help tweak our model because we know the answer ahead of time. So they're really good examples to build our model off of. Okay, so that's supervised learning. And this example is circle not in the prediction because it's not part of the test data, even though it's in the labeled data. No, it just not necessarily. It just means that like we learn against all of these examples that have these answers. And then when we observe new examples, we can try to predict what those would be based on what we've seen before. So if there was it's just a coincidence. We only have two examples in our test data. Like we could have a circle here, in which case we would predict circle. That's fine. Or at least we would hope our model would predict circle, right? That's what we're hoping. May or may not get it right. Um, but it's only not there because we only like we're just assuming that we only have two examples we're testing against. But in reality, we would probably do a lot more than two. It's just a coincidence, really. In reality, we would test against a lot more data. And we're actually going to see why we would do that. Like, why would we train our model and then kind of use additional data to evaluate it? It's actually really important that we do that step to get a sense of how good our model is before we take it out in the real world. So if we apply our model that we build on our label data to this kind of set of test data that we haven't been exposed to before, it helps give us a sense of how good is our model. So it's test data is usually used for evaluation. So that's something we'll study. How do we train? It depends on the model. So training will be an algorithm that will basically update the model according to the data, these labeled examples. Every model is going to be different in exactly how it trains. So we're gonna talk about that when we get to the individual models that we'll study. But loosely speaking, they're going to use the data to adjust itself. Like imagine adjust like tuning a bunch of knobs. Um, Like the best example I can give you is I think I did this one last week where you have kind of a function that predicts the price. And let's say it has weights like weight one with feature one, weight two with feature two, weight three with feature three. So imagine we had three input features and we built an answer according to that. Essentially, what we would do to train the model is adjust these in order to get this correct based on our labeled examples. Okay. So that's something we're going to learn about coming up shortly when we actually dive into model. Every model is going to be slightly different in how it trains. But at a high level, it's going to use the training data with those examples, right? The labeled examples to help guide the formula essentially to adjust to generate the proper kind of model here. These things are going to be adjusted according to the data in order to produce the correct output. So think about these as knobs that will turn. Okay. Which type of machine learning is used? Probably supervised, which is what we're talking about now. So probably supervised because most people want to um, build some type of model to predict something. So yeah, I'd say supervised. Yes, we are definitely going to learn how to train. Yeah, we'll see, we'll do the code. I'll tell you about how it's done. Yeah, we're definitely going to learn it. But what I was saying is that it's kind of on a model by model basis. So I want to wait till we get into the individual models, then we'll talk about how they're trained. But yeah, we'll learn how to do that. But yeah, supervised is used all over the place. Even for generative models, they use supervised learning because like an LLM is going to use labeled examples in order to train, right? In order to train how to generate responses according to prompts. Um, it needs to learn against a lot of text examples. So that supervised learning is what results in that model, right? Learning from those labeled examples. Okay. It is, yeah. Image, a lot of image processing is supervised, like object detection. So the YOLO model is an object detection model, yes. Because it has to be trained, right? Uh, it has to be trained on images with labels such as this is what object is in this image, this is the box around the object. Yes. So if if it ever uses label data to train and build the model, it is supervised. So YOLO is definitely supervised. And we will cover the YOLO model later on in our deep learning course. We talk about object detection. So we'll study that. But yeah, it's supervised. Okay, so on the slide, we have some common supervised learning algorithms that we will study. So all of these we will study and understand what they do and how they work, but just giving you some to name them. Linear regression is kind of the one I just drew out, which is this is the prototypical, like easiest to understand model that is kind of the exactly like this, where we have a weight times a feature, a weight times a feature, and then a weight times a feature, and on and on and on. You can have as many as you want. That is a linear regression, and so that's a supervised model because we need this value here, and we need all of our inputs in order to actually train this model and generate all those weights. um, that that uses labeled examples to help tune all those knobs. Same with all these other models. So we're going to talk about decision trees. We're going to talk about logistic regression and SVMs, which are support vector machines. We'll talk about all of those, but they're all examples of supervised learning. Okay, we'll talk about all of these. They're all supervised because they all require labeled examples in order to train them and then subsequently use them. Okay. Okay, so what are some use case examples? So for instance, in supervised learning, we may be predicting temperature based on yearly temperature trends. So we would have that yearly data as our labeled examples, and those would supervise the learning of a model that predicts temperature. Same thing with predicting crop yield based on seasonal crop quality changes. So maybe we have a bunch of features relating to crop quality. We could predict crop yield. We would just need historical examples with those labels, right? What the crop yield is for each time period, let's say. We would just need those supervised examples and we could easily build a model off of it. Um, this last one, sorting waste based on known waste items and their corresponding waste types. That's kind of like spam. It's like filtering basically, like a spam filtering. So think of it like the shapes example. We sorting things into squares, circles, triangles. Same kind of idea here, where we have a bunch of examples on what those waste items should belong to, like what waste bins they would go to, for example. Um, and those could be labeled, and therefore then we could understand what category of waste they belong to. Same thing with spam. Something is fraud or not fraud, spam or not spam, cancer or not cancer. All of those are going to be supervised learning examples because they're going to require, in order to train them, they're going to require data that has those labels. Okay, so anything that has labels is going to be supervised learning. So again, this is where we will spend probably the majority of our time is doing supervised learning problems, ones that we have labeled data, we're building a model and we're going to predict those labels essentially. Okay. Before we go to unsupervised, any questions about supervised? Okay. All right. So supervised requires labels in order to have an example to go off of to build your model. And that's because you're predicting those kind of outcomes like spam or not spam, cancer or not cancer. Now, unsupervised learning is completely different. It's the opposite. So, unsupervised learning is where we do not use labels whatsoever. So, we're not using any labels at all. So, it can be completely unlabeled, or even if it's labeled, we're not using labels in any way. But we primarily would say it's unlabeled data. We have no guidance because we're not using the labels in any way. We have no guidance to predict anything, but that's because we're not really predicting anything in unsupervised learning. Generally, what we're doing is looking for some structure or pattern. Okay, with unsupervised learning, we're looking for some structure or pattern. So, one type of example that's very, very popular is going to be this second one, which is identification of user groups based on similarities or commonalities. Now, this is going to be a problem basically known as clustering, and it's a problem we will study quite a bit. There's going to turn out to be lots of different algorithms that can accomplish clustering. So what clustering attempts to do is basically say we have data that's like this, and then data over here, and then data over here. Let's just group these together. So like this should be one group, this should be one group, and this should be one group. And we can find those structures and say, okay, this is group one, this is group two, and this is group three. One, two, three. And we can basically build what we would call clusters of data based on how close together the points are kind of located in these kind of cluster zones, like these boxes I've drawn. Okay. Now, that doesn't require any label to do, which is really fascinating. So unsupervised, you don't need any label at all to accomplish the algorithm. So clustering is one good example. Finding outliers or anomalies is another. So we don't necessarily have any label of what is an outlier or what is an anomaly. We are deriving that from the features alone. There's no guidance, there's no label to doing like outlier detection or anomaly detection. Okay, so that's another good example. One that's not listed on here, but is also really important that we will study is something known as dimensionality reduction. So dim reduction. And what this focuses on is basically compressing the data set a bit. So we take our data and basically compress it so that, but we do it in such a way that we retain as much information as we can. It's a very like smart compression. And what it does is it lowers the dimension. Dimension, think of the dimension as like number of columns, number of columns. So imagine we had 100 columns in a data frame. What we could do is actually reduce that down to 10. So like 10% of that. So we reduce it down to 10. And but those 10 are, it's not like we chopped out 90 other columns. We smartly kind of compressed all that information into these 10 new columns that are compressed versions of the 100 that we used to have. So dimensionality reduction is another unsupervised technique. It requires no guidance, no label to do, but is a really useful technique to reduce the size of your data if you're doing things with it. So this is another one that we'll study how to do it and basically more details behind it, what the algorithms are. So probably those two in unsupervised, we'll spend the most amount of time on clustering and dimensionality reduction. And supervised if some data is present, but we didn't label it, means in the example, we had circle, triangle, square. In the training data, we add pentagon. But we didn't label that in that case. Yeah, so every in supervised learning, every row, think about it as like every row in our data frame needs to have a label associated to it. It needs to have a column that represents the label. So if we've never seen Pentagon before, I can't use that as a label. So the Pentagon has to exist in the data if I'm going to be able to predict it. Right. So it can't predict. Right. If we've never seen it before, we have no examples to go off of. We have no guidance. So how could we predict that? Right. We can't predict it. If it's in there, so if we have labels of Pentagon, let's say, then yeah, we could predict Pentagon. We could remove what? We wouldn't go to Pentagon. We wouldn't remove that. No. Let me go back to that page. We wouldn't remove it. It's just if it's not in our labels, we're not going to be able to predict it. So Pentagon's a good example here. Uh, Pentagon is not one of our labels. So it currently is not in our data set as one of the labels. We only have either triangle, circle, or a square. We don't have Pentagon. So I would never be able to predict Pentagon. I'll never be able to do that if I haven't seen examples of it before. Okay. But let's say we had that in there. So we have Pentagon. So if we have Pentagon, we could have an example of it in our labels. But yeah, then we predict it. Yeah, yeah. Don't worry about the test data. The test data is just saying, here's a shape. What is it? Okay, that's a square. Here's a shape. What is it? Okay, that's a triangle. And we could have as many of those examples as we want in our test data. So circle it. Okay, what's this? Should circle. Right? The test data can be whatever it wants. But yeah, if we've never come before, we're never gonna be able to predict it. Yeah, the label data and labels are basically talking about this thing. The labels just mean what are the categories that are present in data. So in this data, we live. So the labels are relative to our data, right? Saying what labels, excuse me, what labels do we have? And we only have a circle, triangle, square. So Penny not part of those labels, we couldn't pick it. No, so unsupervised is not going to make a prediction. That's the big difference with unsupervised. They're not going to make a prediction like this. So unsupervised is not going to make a prediction. It's going to do something different, like basically say like these guys are similar, they're similar, they're similar. There's a cluster, there's a cluster, there's a cluster. It's not going to make a prediction. That's what supervised learning does. Clustering, yes. It is unsupervised, yes. Clustering does not require any labels. Unsupervised means we have any labels, we don't require any labels. So the other thing unsupervised might do is it might say, and without labels, it might say that this is an outlier. It might say that this is an outlier, there's only one of those, and not the other. So that's something that unsupervised could do. It yeah, yes and no. It kind of like a cluster in the sense that it would basically assign a number to it. This is cluster one. This is cluster two. This is cluster three. It'll assign a number to it. That's very meaningful. It's not assigned like a prediction label in the traditional sense of a label. It does provide like a numerical index for the cluster because what we want to know is like, okay, this guy has the cluster one. This guy belongs to cluster one. This guy belongs to cluster one. This guy belongs to cluster two. This guy belongs to cluster two. Does that make sense? So you see some like index of what cluster you belong to. So kind of label, but in not traditional prediction sense. Okay. Very good. Again, unsupervised, no labels. You're doing things like identifying clusters, identifying outliers, doing dimension validation. These are all like structure pattern oriented things. They're not predictions of a label. Okay, they're not, which is what we would see in supervised learning. Okay. So an example would be that we put in the data, we can group together data sets of images into categories, which would be like those clusters. So these would be groups that we don't have any label ahead of time. Like we don't say that this image should belong to this image should belong to this. We derive that from the characteristics of the data. So like a good example is customer groups. So we would identify customers based on like, okay, do they have similar spending levels? How many days do they go shopping in a week? How much money do they spend? And we can kind of group together customers based on similar qualities. Clustering will find those groups that should exist. It will discover those groups based on the similarities in the data. But there's no labels that say like this person should be in this group, this person should be in this ahead of time. There's no labels of that. It's arrived during the algorithm. It's unsupervised. Right? There's no unsupervised really means guidance. There's no guidance to do it. You just arrive that from the structure of the data, which is the layers. Okay. All right. So we had supervised, which uses the labels. We have unsupervised, which uses no labels, looking for structure. And then we have some that's kind of in between, which is what's known as semi-supervised learning. And this is where you use a combination of a little bit of labeled data, but most of your data is actually unlabeled data. And you try to get some use out of that labeled data in order to build a model out of it. And so it uses the label data to generally provide some guidance on usually what happens in supervised learning is you use your label data to kind of predict what label should be on label data, and then you can go from there. So you can create artificial labels on this label data, and then you can use all of the label like a supervised learning approach. So this basically refers to the fact that you start out with most of your data not being labeled. You do have some label examples, and what you do is basically extrapolate those labels into the unlabeled data set, and then provide some artificial labels, and then now everything has labeled in supervised learning. Okay. So it falls between supervised and unsupervised, and so it's kind of rare. Most of the time, you're not going to do that. You're actually just going to prefer to start with all label data. That's usually the preferred approach. Most of the time, you'll actually be doing supervised learning, not really semi-supervised learning. So it's pretty rare. But, it could, like, if you had a lot of examples and we went and so they weren't labeled, and then we tried to guess what kind of shape they were, and provide an artificial label, and then use that whole data set to build a model off of. It falls into that category. Going to the question, they still use kind of label age gender. They do those aren't really labels, that's the features. They still use the core features of the data. They just don't have any like labels in the traditional sense of label. Like you should think of a label as something we're trying to predict. Whether that's a price, whether it's like a category of not or something we've been kind of predicting. And so in our data, we have answer for every row. We have the result, the outcome answer that we're trying to predict. That's the label. So in unsupervised, we don't have any labels. We have the features like gender, age, income, square footage, and bathroom listing. Okay. So we have semi-supervised that falls between. The reason it falls between is because there's a decent amount of data that's unlabeled. What we can do is try to take what we have from existing labels and predict our artificial label, and then use all that together in kind of a supervised fashion for a model down the road. So kind of bigger, is you can try to take, maybe we try to infer some labels based on, we have some labeled data here. We have most of our data is unlabeled, and we try to supply some labels to it. Like maybe we have data category between youth and adults, and we take our labels and we try to extrapolate into artificial labels for this unlabeled data so that we can use it. Because then everything has a label at this point, and then we can just go ahead and do supervised learning from there. We can do supervised from there. What we prefer doing, what we'll do in this course, is just start with supervised. We'll just start with labels. We won't try to derive artificial labels usually. We just start with labels. So one example in the world is like Google Photos, which when you take a picture and provide labels based on previous images in your library, so you can put tags or labels on those. Generally, we take that picture, it's kind of unlabeled unless you go in and specifically provide some tags and some labels. But if you do that, you can still create one of those based on the other label that you have. That's simple. All right, last one, in terms of we have supervised, we have unsupervised, semi-supervised, which we make sure it has some data. Now we're going to talk reinforcement learning, which is completely different. It's different. It's a learning where we actually learn from interaction with the environment. That's what are we learning? We are learning what actions to take in the environment, and we do that by reinforcing positive actions that lead to a reward. So that's where the word reinforcement comes from. Is we basically imagine a child that's from trying to crawl and walk and falling. Eventually learn how to do it and they get a reward. Reinforce some of those positive movements that lead them to walk or crawl. We might learn from penalties. They might learn from some sort of feedback. So they can fall down other such support stuff a little bit, right? Be a little coordinated. So that they learn from those actions in the environment. So this is a comment where essentially it deals a lot with again taking actions. Usually we take action, something changes in the environment. Then you kind of observe some feedback. So think about like another game where you're trying to figure out what move you should make, or another example is with a robot. Trying to navigate a maze to like what direction to take, move forward, move backwards, move left, right. Those are different actions it can take. Also like a self-driving car, it's turned, it's slow down, things that have been trained from reinforcement. So real example, like a board game, a reward like if you win the game, or if you like capture a piece in checkers or chess, a reward penalty would be like you lose the game or lose one of your pieces. That could be a penalty. In a board game, or like a robot navigation task, if you get rewards for moving in the right direction towards the exit, like let's say you want to train a robot to open the door and navigate a room, you would penalize it for bumping into the wall. You would give it a reward for moving. Usually, usually it's a set function. Usually a description that kind of thing in a state. So the word it could be like depending on the board game example, the word could be like, or even a maze. Let's say like navigating a maze. Let's say this was edit. This was entrance. Then if they make it to here, make a miracle. If they get a miracle like plus 100, say, so this is a number. And if they bump it here, let's say this kind of like a trap, this is like minus 100. So it could be like discrete numerical value, could be the reward. If we're moving in the right direction, let's say we encourage like then we can get smaller intermediate rewards. Like this should be a plus, like move forward. This is a plus 5, this is a plus 10, this is a plus 15. If you're moving the wrong direction, that would like a minus 5 or minus 10. So it's like pretty numerical in nature, and what we're trying to do is collect the most reward, trying to get the largest reward we can. For trial and error. So you try this out many times. You basically simulate running through this maze many times, and it's like where I should go is based on what I've observed in the past. It's also about remembering like, okay, what move should I make from space? If I'm here, which way should I go? Should I down? Should I go right? Should I go left? You could know that from experience. So it makes sense based on the reward that I've seen in the past. Like when I've moved down, I've never really moved right. That's it's a numerical value reward. Yeah, that's a great question. How does it differentiate based on gain and knowledge? So it's complicated to answer. Like, essentially so in the chess word, usually where like every space is a state. So I could be in the state, and then it's not only based on where all the other pieces are. So there's lots of states that are possible. So there's a way to quantify essentially what's the value of moving my piece left, moving right, moving it up or down, given the rest of the state. You're right, it'd be beneficial to sacrifice. But we would learn that experience that okay, the best movement is to sacrifice. but we have to learn how to many times. Is to say, like, okay, if I'm in this current state of the world, right, all these pieces are distributed in this way. The best move for me right now in the long run, to get the most reward in the long run, is to sacrifice these right into like a bad position theoretically. But we know from experience that the most long term reward position, like, maybe the best action for me. So I learned how to take actions. And actions are usually like move right, move left, move down. If you buy yourself a car though, that'd be like slow down, feet up, turn the wheel, degrees, kind of actions. So the point is, there's a calculation there that you learn what long term every state is, every state. And you're trying to basically say what action to take from state, given that current state of the world. And I'm really looking forward to actually probably my favorite field of machine learning. Unfortunately, we won't be covering our main course. We have other machine learning in the past, so stay tuned. Maybe at the end of the program, we'll cover that one. And if enough people sign up for it, we'll run it. But it's not we don't really cover yours for our main topics. It's more than something we'll cover. But I really enjoy it. It's very fascinating. Okay, so all this kind of illustrating that saying is you have like the thing that's rotating the environment, like the robot or the car or the human is known as the agent. It's interacting with the environment by taking action of the state of the environment. So that's why you see the state here. It's the next action. Really what we're trying to do is learn the best action. We'll get action. And the best action is one that leads to the most long-term reward. That's the best action. So you have to learn what leads to a good reward by kind of experiencing this over and over again. So there's a lot of kind of simulation or letting the robot try something a lot in order to kind of learn what we're again, I think it's like how you kind of let them try things, they learn what that can be what they do. That's action. Right? So if you're having to place, I said looking at self-driving cars or robotics or machine learning, when we just into recently recommendation systems have kind of learning, and this is because you imagine this built-in reward for you clicking on a video and watching it. So it kind of reinforces that recognition, and that's where you can kind of make similar things to see actual rewarding, enjoy separate rates, time or watching or whatever. So if you're learning happens to a lot of areas, recommendations being one of them. Because just in natural thinking, like what should I recommend? Then it goes reward. In this case, the reward's kind of related to did they count it or not, or how long did they watch longer? It's more rewarding. Those things. But places where we have used and software games. So one of the most famous examples, if you want to get busy, AlphaGo, Zookeeper, the IO, Algorithm was a recent learning bot at the some of the world's best ability to know the board game. That is a little bit more complex than chess, has more word, more pieces to it. They really recently powered by actually learn how to game. So effectively, world kind of masters of games was pretty amazing. That's AlphaGo and Google DeepMind and 2016. That was only 2 years ago. Certain recommendation, you know, correct. Learning to click what is this question to generate a word, which like set that pressure, you reject the penalty. So we're learning how to do these problems very successfully. That's the technique that we will use. So of course we rely on these leading already on to things like NumPy, do numerical calculations. Matplotlib playing not only Matplotlib keyboard as well, also to do bonding. Pandas is the one because that's all these going to be integrated before it goes online. So all of this we learn from Pandas is going to be applied during this course. The actual models. Of course, these old ones are going to be a bit still very useful here in knowledge stage. Mainly for reasons of mostly they're prepared to do some modeling. I need to visualize it before we do modeling because that's what's like those things. Sci is sometimes useful for certain processing unsupervised, like Scikit-learn, and going to help do that. So you here and there, we see before process to use in there. Some of the stuff out there, but the package we use by far most in course is going to be Scikit-learn. Was here, and we've already seen a little bit about Scikit-learn in terms of pre-processing capability. So we use the max scalar and standard from there. Pre-process model Scikit-learn, like it has many different models built into it that we use to help do our training predictions. So it's incredibly machine learning. It's learning library. If you're anything in machine learning, we expected that you know how to do Scikit-learn. Now, what's really about that is that Scikit-learn is a really easy package to do. Really, everything learned was all the same pattern, so the code extremely limited package of making it really user friendly. It's really fantastic. Really more rapid as we go. Any model build to use Scikit-learn. Not only model, doing training predictions and doing the evaluation will all come from it. Scikit-learn models will be really nice and a big solution to that package, of course. So if anything will come away from this course as Scikit-learn experts, will be very nice. This is one for us. Scikit-learn will be a lot of it. Okay. Right, so just that lesson from us three. Network learning data, which is included in the but the also included under it's still data, but it's learning using neural networks. Network supervised, unsupervised, semi-supervised, and reinforcement. So the different users out there. And then Python Pandas. We use mainly Scikit-learn. First, our data, but Scikit-learn will be our go-to for engineering. Right, so that's cool, guys. So let me show you guys which one best describes engineering. Which choice you makes the best justice. And be the correct choice. So machine learning is definitely a subset of AI. It's not of course, learning from experience, and of course, experience is related data. So it's also easy learning from rules, and it's not just used for speed recognition. It uses other things. So A is the best choice there. We say here. Okay, what do you guys see with this? Which example illustrates machine learning to enhance customer experience in an e-commerce company? Before we some typical use case of machine learning. Good. C is a good answer here. Only C. So C is going to do fraud transactions. So that'll be a prediction, probably is running right if this is fraud or not fraud. And then based on behavior, that'd be unsupervised. So we get customers them based on our data, like their shopping behavior and characteristics. That might be unsupervised. But either way, it's machine learning. Okay. My final distinction is deep learning from machine learning and artificial intelligence. So what's unique about deep learning? So you use neural networks as they're right about that. Neural that's what makes it unique. So machine learning, is focused on learning from data. Underneath that is learning and using neural networks, what deep learning is. Great. All right, let's go to lesson 3. And so let's do mode when you start 3.1. So we'll open that. We're going to go to it now. You're going to open that. So to open the 3.1 book, there's 2 of them. We'll see how far we can do the second one today. Probably will. But we're going to do the 3.1. What do you guys have to put in your deals for this course? We move it on. You guys have it? Okay. All right. So we're going to start by talking about supervising. We are supervised and unsupervised after you do supervised. It's going to be a lot of color with supervised, mainly because there are two different types of volume tackle, which will be different kind of values. Talk about what we're hoping to learn here, which is talk about different problems that we'll study, which are these categories of supervised learning. Those two categories are going to be called classification and regression. We'll talk about those and their differences, and then applications and some example algorithms. And that's just within this notebook. 3.2 get into regression in particular, which will be very interesting. Okay, so that'll be first models that we'll go into 3.2. It's good supervised learning where we learn from labeled data. So we have input outputs in our data set. So you train a model on this data, input features, and corresponding outputs that are the labels, right? So the goal is to learn a relationship between the input and output. Of course, that's what a model will do. And what allows us to do is then get a model and use a predictive never before seen data, right? So then we have predictive model that we use for new samples. So remember, we will have data in our columns, and then we learn those the label work and predict. And our model tries to learn some measures and the output. That would be the final product, consider a price, and those kind of things. So let's start that. Inside of supervised there are two types of learning that we do, and they're based on the label or sometimes we'll the target measurement. And depending on the type, we get these two categories of learning. One is regression, so that's generally we are making something that is continuous, something that is a numerical value. So think of price, temperature, value, predict something like that, versus something that's categorical. So that picking something categorical will be a fraud. Those are discrete categories. And the problem with categories is known as classification because we're trying to classify examples as belonging to one category or another. So we have two main types of supervised problems: regression and classification. And they're going to be handled separately for many reasons. Occur. The primary reason is that we're making something continuous and regression based on discrete. So the models have to be studied about that. But then beyond that is the evaluation has to be different too. We'll do this also regression theory to take exact numerical answer. So generally we don't care about we don't care about getting exactly we just care about getting it nearby, getting close enough. We do care about exactly the discrete category. So we'll evaluate that differently. Say in our regression to be close because we assume it's a continuous number. Okay. The question on that. So classification is creating something categorical, regression is creating something that is continuous. So if you're trying to process singular features, talk about flow, and bathroom, all these price, the regression problem is continuous value. So look here. And you're trying to predict the temperature tomorrow. That's your regression problem. We're just learning because trying to predict a numeric temperature. Okay. And this category, this category, this classification, the regression of the classification. Right. Classification. Because we are predicting those two categories. It's just hot or cold. Now we're not saying if the threshold is hot or cold. That would be a decision on what my various mean. But we only have two choices: hot or cold. Versus predicting temperature would be numerical prediction of the same factor. Right. So that'd be a regression and then a classification. Now, it's a complete number of category. But evaluation, like if the true answer was before and that's super close, pretty close. And from a perspective, that's good. Whereas if cold, that's the wrong answer. The value is like different. That's what we see as we talk about evaluation of our models. Is time classification regression is value. You can see a physical say, we know exactly for maybe a model number. That's a different count exactly number. So let's how to look at it. Let's see something like here. This here that. The back end, I guess we're close. That's better. That's pretty close. We're going to that would be possibly. Any question on this? Next on classification. What is the first as we belong? So we're going to do classification for category. And then different models that do that. Different use regression, model use classification. Right. Let's talk about application here. So just need to we have a imaginary data. So it's going to help by getting recommendations and that's quite today. And it's kind of like how we have this would be multiple applications. So there's no need of getting a category of their classification to be reject the candidate. Finance, you see this all the time with things like this and loan approvals. You can predict the degree of if loan application, that would be a classification. We'll see about classification in a way. So it says here, we can predict the length of the loan we made. There's a lot of classifications. We say predict the category, but under the hood, they actually predict probability into a category. Like we can say, we say the loan very low, but it's less than 50% probability. Then we label that if it's greater than 50%, then we label that. So we set it and say, truly predicting the model, say probability, but into a category, financially, less than 50%, we should greater than 50%. Okay, so that's what we see some classification models is actually the ability to turn that into a category label. And just think simple as play for a moment for the category. So if I use all the plays, I'm using fraud classification, predicting sales revenue, that'd be a regression, right? This revenue next words, that's gonna be a regression problem. Email is the same thing, that'd be a classification. That's copy that's when you take a text input and put this email the same word. That'd be a supervised problem, that'd be a classification problem. Right. You have to measure using and quality classifier process grade factory as well. So something that happens is we have to online and we just predict quality, volume, quality. So this is classification. We're going to different category quality. So if I'm going to maybe we'll try some QA for quality control stress. So that's a classification. So in regression, we use the current current level and I can use forecast assignment. So we look for regression models I use to predict kind of in this case levels. So that's it. Classification. Each of these examples. Regression is kind of a problem where you are examples thing that you have to review and you have to predict with one feature. Regression is learning and it's the classification. So it's a number of shows or one watch. And so we'll see here. We'll models in regression. All right. So we're to the actual models and also the models we're going to cover. And they are really different in purpose and their what problems they're used for. And they're how actually treating different. But at a level, they're all doing the same thing. We just learn some relationship input data in the label. They look at supervised. They have those labels. They build so much there. They just do it. And what we're going to study is some models where you find them using but they're all trying to learn some of the features and the output. Just they're trying to learn it. They just do it in place. Okay, so as we all learn about models, more details, we'll learn in-house. But they're all trying to learn that. They're trying to be able to make predictions on video. So here's a list of models we will cover and we'll talk about the system. Bringing them all in one thing, but first we're going to start with that we'll cover today is the linear regression. So we will regression and we'll cover the rest of these guys mostly in context of classification. So what's interesting is some of these guys have used both for regression, just we certain systems. They have regression classification and regression tracing. But we're going to start with regression today and work our way through the rest of these models. We're going to start on 4 classifications. These all take from 4. And then we'll do this by lesson 3 and through 2. We'll do all about linear regression. So linear regression is this actually that's the regression classification. But the reason is that this regression computes a probability. So it's a regression to predict number of probability. So it's really between obviously 1. So it we can probably probability like I'm saying fraud. But so it's it's so regression predicting is probably. So for classification primarily. So we'll say 4. That's why it's on that kind of location. It's pretty probably if you can turn into a category. As long as you probably is the right way. Like probably same, probably not. Okay. So regression for all these cases because we haven't really modeled yet. So they're good. I think it's good. We haven't yet. So let's come back inside these examples, guys, to see why it makes sense. But for regression, just full context. Look at examples. So we like predicting the house cases that we see in that house set. So if we went to estimate the house price, we do that by using feature size rather than survey addition, property, and then you can estimate price on those features. So regression is going to be process mechanics. Not practice that in the next book. So we'll there's just other models again. So I don't really go through those until we get to those models. So we need to come back and make example. K and used for so cluster model is going to be different. It's going to be K means. So there's K nears. K nears is used for regression classification. So we'll talk about K nears later in before. It's not really more, yeah. So K needs clustering algorithm. That's it. There's a use now. K nears is a supervised algorithm uses levels. Any just different. So let's go to the figure two. So that will be our first discussion around regression. So thanks to regression. Please let me go next. So focus on regression first, and then we'll have applications more. Which we'll put all the models we use application. We're going to talk about regression first. So pages to go through a lot of material here around regression. We're going to start with linear regression and see how we can what that model is doing. But you kind of see the idea of it a little bit already, so it should be somewhat familiar. And then we'll talk about how to adapt that idea to what's called nonlinear regression, using polynomial features. And then they talk about evaluating onto it. It would be exactly evaluating and interpreting that would be there because we want to know the performance of that model once we have it. Right now, is we're using we need to reach change model. We're talking about how you can do based on performance. And then we'll talk about here a couple things to say evaluation, which is used to perform situations. Whenever the model is performing against the people and people. Necessary to use Scikit-learn and do them. Put all difference between generally a strategy, which is something that we use so I need to today, but quite a bit for that needs to around vision and version. So we'll start with version. Let's start with linear regression here. And really what linear regression is attempting to do, which is this picture, is probably line. It's not a line method. So this is all about and it's really a good predictor. Because if you give me features, if you give me features and say they are, let's say you give me features right here, you have this value like this. Then I know I'm understanding the language, and I will generate a value right here. That's right. I'll line that input, and I can what you see on that line. And what you can see is this line. It needs to estimate data because it says pretty neat. So it guesses what the output should be. Can it it's a good estimate of this line. So our goal linear is kind of the equation of the line. So this equation of this line is going to be our yes, it looks like here. So if that would be more than because you have generally more features as a feature, more than generally looks like this. And plus here. Plus yeah. So look at that. So yeah, that's idea. Right. Look. So yeah, you trace we're talking about the best model here and you know regression to extend the regression. So yes, you do nonlinear too. So linear is more say that it is now what we should figure out is why is this line a little bigger? And the argument is that if you take this distance from the actual limits, the line is going to be found such that it minimizes the distance from the points to the from the points to the line. So we want this distance to be so we want this distance to be kind of unknown. So we draw a line here because that's a lot of distance, right? So that'll be a lot of error. Contributed from not being able to get the whole very well. We actually that back of the line. So our goal is that this error distance can be at minimum possible, right? We want distance from these points to the line. We want those to be as minimum as possible. Our goal is find so we're going to build a of the line that our error is minimal. And the error there is the distance of our elements to line build. So in order to train this, we'll need to adjust parameters or I think see basically the adjust we make this as small as possible. And that's possible. Okay. So there is regression culture where advertising sales predicting build and trying to manage for regression problem. You know that for inventory everything levels of certain blood markers or like that. Real estate predicting prices foliage and things. So we're going to use and everyone a number in the regression problem. So this regression we're talking about here is generally known as which is linear, as a linear. So and you have a line line is linear, meaning that it is exactly so it's like these feature plus weight feature. And some stuff from this in there. This is linear because all of these are important and linear with the different This is a linear model because it's able to have a linear equation. Right? So we're going to look at linear model. So we have a linear equation. That we're predicting this assumes our model is for this kind of equation, linear equation. This is our model for linear regression. Okay. So you train linear regression. Your goal is to learn these weights. So that you can plug in you can your features and you can generate a rate something line. Right? So you have line. We put in our line. That's all. Okay. Linear model. Why call linear regression? Okay. So use the least criteria as to whether it's clear of this is how you want to line is for this here. So we're going to find the least distance, which is the minimum distance. That's how we find all of these weights. It's minimum, basically minimum using the variable, which is why we have to clear the minimum it's like a problem. Right? We're trying to find minimum of this quantity, we just have this fit line. Okay. So linear and we can do a simple regression feature. So if you have one feature, that's exactly the one input feature. Sometimes it's known as simple regression, linear regression. There's one feature. So linear is feature. And so this equation is supposed to be exactly that you use it was exactly that. I'm just using simple basically exactly that simple line feature. So this line is to outline the coordinate like that's the line of blue dots. This is so this line will be y equals beta 0 plus beta 1. So some weight beta 1 times the only feature we have x1. Okay. So in this case, we create sales. So sales value beta 1 and the feature put in is function of t expenses, which is one feature which is e expense. So on this graph, this is the model. We have a feature and we have these features, b0 and 0 and 1 which applies to the feature. And our model has to be for certain rules. These guys learn during model. So our model and they're going to at least all these squares. Let's try to minimize this. So we want to minimize this line to all these points. Trying to minimize this. But imagine like moving around and turning a slope single S, which we say are those. Okay. So $10 and T expense. T actually is number of sales we have. And T expense is I think it's in dollars. So how much expense we put into the product, and then this is how many sales do we have of that product. So I think it's around. So the blue points are actually points because the collection we have a different that has that has the attributes. So it has the has one set of 120, and then the CFL will be like 700 units, let's say. It has, so this is just our data set, right? This is like a data frame that we have. And then we have ones that were 50, and this could be 400, let's say. And one of our data, and this data is here, right? So these are here, and the red points are our model, in the direction model, we're putting in values here in Chinese, this is your version, right? And that line is derived from, right? It's learned from the derived tables. So that line is derived from the data, learned from unsupervised is learned from it. So you see, you're trying to build this such as this is minimum. So then output fit. Just plug it, just there. See how it goes. For the distance, this should be the distance here. Yeah, actually, it's a distance form. Okay. All right. So we're now we usually have one feature. No, so generally we expand this to a more case. We have more than one feature. Like what we see in how we get, right? Where we could try how many different like factors. So more broadly, instead of simple linear regression, we have what's known as multiple linear regression, which means we have multiple variables or multiple features. So this is exactly like what I've been talking about. So we just came out that one into many features, which is in the intercept term, which is like what is the term? Because the line to try the right place. And this is the equation that we would give the model. This is our model structure, as we would be learning. And it's like, yeah, so if all of these terms are 0, our data, the result will be if basically 0, we'll reduce this as a concept. So it orients so it orients like so these are going to orient the tilt, which includes this or more slopes. That orients very start up. I should slow it here, just around here. That's what we get plus. So this is the direction of the most you guys will have, and these are features. This is your x, this is feature, this is feature, feature, and what you learn during training coefficients, all the coefficients including the 0, we learn, so you learn. Formula, in order to inherit data from using that and that's it. Like, you know, data, kill change that cycle number 4 find that's it. So what we do anyway, but that's the process. Basically, if you're just in a line, you get more level. Thank you. Which like so that's actually where all like I also like inheritance. So this it's pretty interesting about this. But still, it's more general line that's it. It's still the same idea. We're still trying to code the best solution minimum. It's more relates to the all inheritance more and more things. You're not different here. So I'm trying to this goes basically relates to what you guys but we also going on is and find the best value weights that minimizes the line to so now we're trying to make this to use this value to find the rules and we try to convert that same line. There's something that occurs at least make it learn find the best fit function. And use that learn the model, go ahead and find the best and then you know how to model. We plug in different features and generate agent using this style. So that works is a train model and then we can think of it. We plug in the to generate agent. Okay. So let's see how that's going to be super easy. It's like this scenario we have our Pandas are that so we're going to get safety. I don't know if you find safety so okay if you have it great in my file so just these the T and sales column here from data. So to see how it's fit, we're going to do a very standard process for us. We're building out these steps to be very stressed. First of all, slave features label. That's the first thing. Okay. So usually it's taking all those but only the first column and extracting all features from different. We just first column, the TV column, right? That's on there. And our target label, is the second column. It's that sales column. And our first step is to always select parts features from labels. Okay. So all the different and we have all our labels to basically followed by just the labels. The reason why is because we need our feature labels to put in a modeling function. It's are in here orders these are from our answers or labels that by modeling. So there's going to separate those. So this will separate that capital X and lowercase y. It's a very standard equation. Then we start here people called capital X and then you have a lowercase y variable. So standard. So it's standard that X represents features and Y represents labels. Whatever the column is, the sales using the default essentially. Yeah, so it is that we are this is that we are splitting our data. The first reason is the string. It has two columns, TV and sales. For example, I will go ahead and look at data. Yes, so what we're doing with this is our slave part our variable features. This has to contain our features and Y will be our label. This is really back to column here, and then we're having second column will be sales. This is predict sales given the so the first thing I do is split our features and the label. That's the first thing we do. And we have to do that. This is really first our model will expect our data features to be separate from the label. Actually, it's the first column. They're using that right. So all rows are column, which is Y is ordering. Everything else and the value. Y split. So this is the column, right? The different column. It has 0. So you set it earlier from 10 to this, and then data equals EDWCSV. So we're going to do here. Now let's start with we're going to see this over and over and over again. So we're going to come over and over again. And that like this next we call training test split. Which does it take our data and it goes to X or Y data. It puts it into percentage of use training data and a percentage of use test. And why we want to do that is maybe so we can do evaluation. So we build out over here and then we test it on data and see for we reserve a percentage of use test. Usually this data is somewhere between 20%. Somewhere between 20 to 30% of data. So that means the data is used for training. The majority of the X and Y over here is going to be 78%. Generally used for training. Okay. So something between 30, the issue is somewhere in there, we're going to use 30% and 44%. We pick a favorite 30%. We don't want to get so that we can have a fair value. We train on this, turn on this, and then see how the performance is as we go. Right? We're going to take X and split. Using this traditional translate. Do this thing for us. Okay, so someone has a potential translate. That way, we're going to X or Y. We'll have to stage 50%. Going to select to test it, and later that 70% will be used for training model. So what we get, we have this split. We're going to have Y per team test. We're going to get an X train and a Y train. We're going to train features and train labels, and they test features and test answers as labels to do evaluation. So we should be able to here and then analyze it. Meaning take the feature, blame model, and then select it, compare it to data. Right? We should be able to do that evaluation. Okay. And you're wondering, why are we doing that? What's the first step? How do you know this test data? Gives a sense of will our model generalize to new variables. If it performs pretty well on this data, that's what's going to be that's a good data. We use it when we use integer. Right? So this binding position on data that I've not seen before. It's only see the training, right? We're going to train a model on that data. So that model is until evaluation and generate some to see how good it's performing and does that change analysis to never before seen examples. So what we're going to do in the world is we use a new example for model. This is our test, our evaluation. Okay. This is on the regression administrator that code. It's a train test data. The very data that we use per data train and another value. Very data. So this term this engine is called cross value. Because the original data set to two model crossover to a data the testing set. This is our evaluation. This is just a global process context. Usually in many sections. They train the evaluation time. Just another way to process that. This is the simplest way here. So we're going to import from Scikit-learn. We're going to model select module. We're going to use the model select. We're going to get a function, and we're going to use our and we're going to set a size 30%. What size is 30%? 32 small. And there's one free. So that means we're going to set that. Use that on the range state is for reproducibility. because this is the control this is already so yes see I see but it's maybe I don't remember the table anyway we're doing it yes if you choose A over here, your name is important. You choose 0, you 1. Usually positive. If you choose like the industry here, it's still obvious. And with this number, it's so there's no usually you don't see the fine. There's you just usually usually 50 and 1. It's really shocking is everyone's looking at the same. So it's 18 rows in this list. So it's kind of like a it's usually you have entry that you're going to know. Moving that for the so this is what you 40 and 70. This is like it's everyone's looking at and so the data in these sets are acceptable. And do you see how we pass out like we generate four data answer. We're going to change your texture train label methods. We are getting four train label use sets. So we have 3 features, train label, and test features, test label. Okay. So I split it into X and Y. We need to sort work. So each time we only do we only do X and Y and then train split. And we generate data for building our model. Okay. So this data here is what we find in model. So this is what I right. We move that. Okay. We're going to split and actually move it. But this data we split it into X and Y and we split that to train split and then we end up moving have into all train movement. You can run so you can run you run the on the on the train and see how it compares to CR6. So you can do that and see how it's so I think they're really good things that you can control things and things that you out. So we're not going to see the zeros. But this is what you're using. So things that so that's the same usually. So this is about percentage usually for the by 3 level. So you obviously most of the user. Anyway, this is like it's you said that any injury might be a builder. You said you just insurance because this is control the first rows and also into the asset. So you said it's some using this system. So it's like it's not like it's not your data. Using this matters that it wasn't these. Let's do a model. And usually how easy it is to be a model. It's got to be for every single model. We're looking at the same for training it. So we're going to do is import our model. So from Scikit-learn using linear package for the linear model is we're getting linear and we get Scikit-learn here. Okay. So regression and look how easy it is to all Scikit-learn models use the fits point to train. So everyone can use history like regression any of these functions before all of the same terms. It's fit is Scikit-learn very for training model. So it's 16 so and what linear regression is at least 60 here to find it. There's trying to get amount of squares from one that is trying to build data. And what we notice we can do same way data between features and training labels as supervised. So of course we put in the labels, right? Of course we use labels here and we're doing here. So in all labels for our needs it is fit into train model. So we can use it for you. Okay, basically that's present predicted. It's in the training here using blocks. And then this doesn't fit. It's not easy to use, right? So now that we train model, that's how we fit. Now we use the work on to fit. There's a lot of on there to do these and find these and to realign. So it's working on it. But Scikit-learn is training for us, right? That's fit. Really and we can see the question actually use here regression into space. I'll go through that network. So this gives us a training with for instance, right now exposure. This only have one margin, so I have to go and it gives us with this. This is weights. And so we have the okay. But you have features, not features. More features. This is C1, C3, and the is over. That's the next one. There's another just like use my demo. Plus then what you think. This is only what we need to do. And you run this, we run it. Right. So now, and you just do this. And so that's your next. We have your we have to build a sort of test data. So we have our test data here. And we're going to use our data and plot. We're going to use the this is our sales prediction. This is how we use data models. You know, it's trained. We'll just use it. And consider data features and trace rate pretty well. Every one of these features is different. Built into these models. So we're going to use plots. Are reading features and the see how we fit that really was. So see this fit. Okay. So here's we have all our data. We have our blue is our training line. We build our models pretty deep. And then our data here. We're going to use this is right. We can actually by more picture. We run it and we're going to right for data sales. Apply that on y-axis. So they'll be predictive. This is all method. This is all again. This is all right. These are nice. This is the best one. So it tells you to fit models later whereas that makes you think so when you're not fit, train it, and then you're not fit, and then never fit out. So what it's doing is between this point. We are so we could do so when you plot so plot out we are going to do a set on your test. So it's still like feature the line is missing. But the code shows the same line just feature it was. Then you this is better because this is not fit through this data. That makes sense to do bring that set. Yeah, I can go do I can do here and train how I do it. We're going to do this idea and I'm going to sit on the same plot. That's all we're going to do, right? Yeah, I did the same. Yes. So the line values the test predictions equals test values are not test and we try our test predictions. Yeah, we see the actuals are on this. Yeah, so we'll do you learn how to evaluate this. Yeah, you will do that. We just learn how to do correlation. But it's not here. So you're good. Right. The idea is not to train it and then predict you that doctors monsters use all and predict it. So here's what we know is the line. This is not fully right. This question, I'm sure there is. There goes. There's not really no. You look at the source code, you really need to have fun. Anyway, so here's the use using this one to we're using predictive. How I use it is a iterate through iteration to update according to a certain basic gradient of the error function. Error function is the series from the line to false. So you can grade that and do predictive a little bit. I'm going to do some research on linear regression to see how this happens. It's pretty cool here, and you have the notion that you want to minimize the loss with error. This case, the loss is squared distance. So it's like there's a small square distance on your prediction. For your label model, which is the B0 1 1 2 2 and square distance. You're minimizing that. You focus on this is a this is how you grade this is different. You're going to have to know it. So what you see happening now? Really fun version of based on equation. I'm saying I have a first over. I have to talk about over numbers. Really that lead to the clean axiom for division. And simply the division not neutral ways and the division with so it's where the model is more than so well it's full general so what is this actually so it's next like we would actually for deliver on data. Let's talk about that data. That means that model is overfitting to data and it's not in general. So my first idea is you can start to get algorithm. So we actually have all the algorithm. We want to start with simple. So you're trying to find the model and you have to let you set it up. You can start and then you do this all. So that's what you do. So box based on the needs of the box. So for example, this is like we have a small we can just this is because you don't need full influencing people that on that previous influence on the different variables. So we have to start to the project and on the actual this is I'm going to show you how to use also the mobile is what's the layout so same thing you have all in the whole if you change that no shopping again try to do as you want to make this sure you have to research also the information to watch me never start please get that different category for action one of the actual tables here I'm going to try to solve this so in terms of the vision you have to you know use people in all that have a measure process so this is going to be right now this is basically the whole so I think you're also seeing the powerful